The plan for today is to continue talking about generative adversarial networks. As a recap, remember that the nice thing about generative adversarial networks is that it allows us to train models in a likelihood-free way, which basically means that you no longer have to choose kind of like special architectures or factorize a distribution according to chain rule, because you're sort of like forced to be able to evaluate the probability of each data point because you want to train by maximum likelihood. The idea is that there are ways to basically compare the probability distribution of your generative model to the data distribution. That it does not involve KL divergence and does not require basically you having to evaluate the probability of samples according to your model. And in particular, we've seen that there is one very reasonable way of figuring out how well your generative model matches data distribution, and that involves basically training a classifier, and the classifier is often called a discriminator in this space. And the discriminator is supposed to, is trained to distinguish kind of like whether or not the samples it's receiving are real, meaning they come from the data distribution, or fake, meaning they come from the model distribution. And you can think of the performance of this classifier as an indicator of how well your generative model has been trained, or how similar the samples it produces are to the real data distribution. If the discriminator is having a very, very hard time distinguishing your samples from the real ones, there is a good chance that your samples are actually pretty good. And so based on this intuition, we have this kind of training objective here, which involves a minimax game. So it's kind of like an optimization problem where there are two players. There is a generator that is trying to produce samples. That's your generative model. There is a discriminator D that is trying to distinguish real samples from fake samples. And there is this performance metric, which is basically the loss of the discriminator. It's just basically the negative cross-entropy loss of the discriminator on this task of distinguishing real versus fake. And you have this minimax game where the discriminator is trying to do as well as it can in this classification problem, binary classification problem. And the generator is trying to make the discriminator perform poorly. So they're playing a kind of like the game, and this is like a minimax game in the sense that they're pushing the objective function in two different directions. And the generator is being trained to try to fool basically the discriminator, trying to produce samples that are as close as possible to the ones in the data as measured by a discriminator not being able to distinguish these two types of samples. And we've seen that under some assumptions, so if you assume that somehow you are able to compute the optimal discriminator, recall that optimal discriminator is basically giving you density ratios. And if you plug that optimal discriminator into this loss function, then you get kind of like a mixture of two types of KL divergences. And we've seen that that divergence has a name. It's called the Jensen-Shannon divergence. And up to scaling and shifts, you can think of this training objective from the perspective of the generator, assuming the discriminator is optimal. You can think of this as trying to minimize this Jensen-Shannon divergence between the data distribution and the model distribution. And so this is not too different from traditional maximum likelihood learning, where we're minimizing KL divergence between the data and the model. Under these assumptions, you're trying to instead minimize some kind of like mixture of KL divergences that are basically between the data and mixtures of models and data.
Why was the shift and the scaling important, considering there isn't much else there? Would the target not be the same?
The shift and scaling is just, it happens to show up if you define the loss this way. Just happens to be the case that Jensen-Shannon divergence is defined that way, and it doesn't have, this is kind of like the optimal loss that you can have. Not super important. It's just like if you work through the math, you get a shift and scale, but yeah, we don't care about of course, like the loss is the same, basically you're just changing the landscape by shifting it, so it doesn't really matter. It just happens to show up if you do the derivation. And in practice, of course, this is not feasible in the sense that you cannot get the optimal discriminator. But in practice, what you would do is you would have two neural networks, a generator and a discriminator, and they play this game. And then the generative distribution is defined as what you get by transforming simple samples from a prior distribution, like a Gaussian, through the generator network, and then you just optimize this sort of objective function. And there's been a lot of success based on this paradigm. This is a cool kind of repo where you can see a lot of different GANs and variants of these ideas that have been proposed in the past. And what we're going to see today is that this idea of sort of like setting up a minimax game is actually very powerful. And not only you can use it to minimize Jensen-Shannon divergence, but you can actually use it as a tool that, under some conditions, allows you to optimize a much broader class of divergences between the data and the model distribution, something called F-divergences. And we'll see that there is also another kind of like extension or similar framework that allows you to approximately minimize some notion of the Wasserstein distance between model and data distribution. And we'll also see how to get latent representations from generative adversarial networks. So similar to a VAE, we'll see to what extent it's possible to essentially not only generate samples, but also map samples to latent representations that then you can use perhaps to do semi-supervised learning or use them on other kinds of downstream tasks. And then we'll also see maybe cycle GANs that sort of like conditional generative adversarial networks are also pretty cool. All right, so first let's go back to the high-level picture. Again, remember that we've been in the first part of the course, we were always kind of like choosing this divergence between the data and the model to be the KL divergence, which plays nicely with kind of like likelihood-based models. If you can evaluate probabilities under your model, comparing similarity in terms of KL divergence makes a lot of sense. And we know that that's kind of like optimal in a certain sense. We've seen that to some extent, you can optimize the Jensen-Shannon divergence through the GAN objective. And what we'll see today is that you can actually optimize a broader class of divergences that are called the F-divergences. And an F-divergence is defined as follows. So if you have two densities, P and Q, you can define a divergence between them by looking at the expectation with respect to the second argument, which is Q, of this F function applied to the density ratio between at each point between P and Q, where F is basically a function, a scalar function that has to be convex, lower semi-continuous, and it has to evaluate to 0 when you plug in 1. And as you change basically this F function, you get different ways of basically comparing how similar P is to Q. And just to be precise, what these technical conditions mean, well, one is that you have the function f has to be convex, which hopefully you know what it means. It means that if the graph basically, if you take 2 points and you connect them, that line is above, sort of like the graph of the function. Has to be lower semi-continuous, which is just a very technical sort of thing. It basically means something similar to continuous. And if it's discontinuous, then kind of like on one of the directions, then it has to be sort of like above the value of the function where there is a discontinuity. Not super important. But the intuition is that somehow f is what tells you how much you're being penalized when P and Q assign different probabilities to one of the possible things that can happen. Let's say one of the possible images. So it's similar in some sense to KL divergence. where remember what we were doing is we were going through all the possible things that can happen, and then we were looking at the ratio of probabilities assigned by P and Q, and then we were taking some kind of log. This is a generalization in the sense that you can use different kind of convex functions to score how happy or unhappy you are with different kinds of density ratios. And ideally, if P and Q are the same, then they are going to assign the same probability to every x, and so the density ratio is 1, and then this function f is going to give you a penalty of 0. And that's kind of like the best that can happen. But f is essentially measuring how much you care about P and Q assigning different probabilities to the various x's, to the various samples that can be generated by the model. And the interesting thing is that because f is convex, then you can still use the same trick that we did for KL divergence to basically show that this F divergence is non-negative. And in particular, because we have an expectation of a convex function of some density ratio, this is always at least as large as the function applied to the expectation. And now that expectation, you can expand it. It's basically the integral with respect to this probability distribution Q of the density ratio, which is just P over Q. So the Q's simplify, and you're left with the integral of P. P is normalized. It evaluates to 1, that integral. And so this is f of 1, which is 0. And so you get the desirable property that basically this F divergence is non-negative for any choice of P and Q. And if you plug in P equals to Q, then these density ratios here are always going to be 1. F of 1 is 0. And so this whole expectation is 0. And so it behaves similarly to KL divergence in the sense that it tells you how similar or different P and Q are by kind of like looking at all these density ratios and scoring them through F. If the distributions are the same, then the density ratios, the two P and Q assign exactly the same probabilities to everything that can happen, and that F divergence is going to be 0. In general, it's going to be non-zero. It's going to be greater than or equal to 0, and so it kind of like makes for a reasonable sort of objective function to try to minimize this quantity. So we could have one of P and Q be the data distribution, the other one be the model distribution. Then we can try to kind of like minimize this as a function of the model. And if you, the nice thing about the F divergences is that if you plug in different types of Fs, you get many existing reasonable kind of divergences that you might want to use to compare probability distributions. For example, if you choose F to be U log U, and you plug it into this formula, then you see that this expression evaluates to the usual KL divergence, where the way you compare two probability distributions P and Q is by going through everything that can happen, look at the density ratios, and scoring them with respect to this log function. There are many other F divergences. So the nice thing is that if you plug in different Fs, you get different divergences. So we have the Jensen-Shannon divergence, which you get by choosing, for example, this kind of odd-looking choice of U. You can get the usual KL divergence by choosing U log U. You can get the reverse KL divergence, where you basically swap the argument of P and Q, and the regular KL divergence by choosing minus log U as the function F, and you can get many more. You can get, you can see here, squared Hellinger, total variation, alpha divergences. A lot of different kind of ways of comparing similarities between P and Q by choosing a different F function. And what will turn out to be the case is that generative adversarial network-like objectives can not only be used to minimize an approximate version of the Jensen-Shannon divergence, which corresponds to a very particular choice of F, but it can actually be used to optimize all of them. So you can pick any F that, according to which satisfies those constraints, that defines a valid F divergence, and what we'll see is that we can use a GAN-like objective to minimize the corresponding F-divergence, approximately. Okay, now the basic setup is that, as usual, we're trying to train a generative model. So we have a data distribution, we have a model distribution, and it would be nice if we could choose an F and then either minimize the F-divergence between the model and the data, or perhaps the F-divergence between data and model. Now this is reasonable because we've seen that for any choice of F that satisfies those constraints, this objective function is non-negative and is going to be 0 if the two arguments match. So if your generative model matches the data distribution, then this loss function is going to be 0, is non-negative. And so if you set up a learning objective where you try to minimize this as a function of theta, you might be able to learn a good generative model. Now, the issue is that the expression, kind of like when we started looking at KL divergence the first time, doesn't look like something you can actually optimize. Doesn't look like something you can evaluate, and doesn't look like something you can actually optimize as a function of theta. First of all, you have an expectation outside with respect to, let's say, the data distribution. Well, we don't know p data, but we have access to samples, so we can approximate that expectation with a sample average. So that's not a problem. The real problem is that you kind of like requires you to evaluate the probability of X under the model and under the data distribution. And even if you have a likelihood-based model, even if you can evaluate p theta, we can never evaluate probabilities under the data distribution. And so that density ratio is unknown. So kind of like in the KL divergence case where we have that log density ratio and we couldn't actually evaluate it, and we could only actually optimize KL divergence up to a shift, up to the entropy of the data. We have the same problem here, that this kind of objective function seems reasonable, but doesn't look like something we can actually optimize. And if you try to swap, you try, okay, maybe we can do, instead of doing F divergence between p theta and p data, we could try to do p data to p theta, and you kind of end up with something similar. We have, again, an expectation with respect to samples drawn from the model, which is fine. But again, you have this density ratio. That is not something we can compute in general, even if you have a likelihood-based model. And so what we need to do is we need to somehow rewrite this F divergence or approximate this expression and write it into something that ideally does not depend on either the probabilities, basically does not require you to be able to evaluate probabilities under the data distribution, and ideally not even according to the model distribution. Because if the objective function does not involve neither p theta nor p data, and it only requires you to be able to sample from both of them, then we're kind of like back in the setup just like a generative adversarial network, where we can basically use any sort of architecture to define p theta implicitly as whatever you get if you were to, sample from a simple prior, feed the samples through a neural network, which is the generator, that defines a potentially very complicated p theta over x, to the extent that we can write down the objective function in an equivalent way or approximately equivalent way that does not require us to evaluate probabilities, then we can use very flexible kind of like network architectures like in generative adversarial networks. Questions? Yeah.
Isn't p data of x like the probability of if you're sampling from p data? Isn't it just
the question is, okay, is p theta p data x 1? And in general, no. That's basically the probability that the model assigns to every possible x. And so, that's just there is an underlying, as usual, kind of data generating process that we assume we have access to only through samples. So we assume we have a training set that was sampled from p data, and that distribution is not uniform. This is not the empirical distribution on the data set, which could be just like 1 over n, where n is the size of the data set. This is the true data generating process. You could set it up, trying to fit the empirical distribution on the data set, but it's not quite. You could even think of that as an approximation of p-data, where you kind of like have a very simple kernel density estimator based on the training set. But that doesn't work particularly well, because in high dimensions, it's going to be, it might not generalize. So you're kind of like overfitting too much to the training set.
Is the reason why you do not even want p theta is to avoid likelihood based learning?
Yes. So, I mean, this machinery works if you can evaluate p theta. But as we know, like evaluating p theta constrains you in the kind of models you can use. You have to then either use autoregressive models, or you have to use invertible neural networks, which is kind of like undesirable. And if you could set up a learning objective where p theta is not even something that you have to evaluate, you just need to be able to sample from it, then that opens up the possibility of using implicit models, like feed noise through a neural network, kind of like a simulator almost, where you don't even need to know how it works. You don't need to know how it assigns probabilities to data points. You just need to be able to sample from it. So that opens up more kind of a broader set of models, including kind of like these implicit ones where you just need to be able to sample from it, essentially.
And you were mentioning that F should be convex, but for the calibrations we have like a log, which is concave.
But it's u log u. Because, yeah.
Just building on, just related to that question, why is the KL divergence? Why do we get KL divergence with u log u? I thought.
Yeah. So the reason we need u log u, because if you remember KL divergence, it's an expectation with respect to p of log p over q.
Oh, but here
But so you have to multiply by, to basically change the expectation to 1 with respect to p. But if you see, in fact, if you want reverse KL, then it's just minus log u. Because reverse KL would be an expectation with respect to the second argument. And so the u in front is basically to change the expectation from 1 under q to 1 under p, basically. Okay, so now let's see how we can actually move forward and come up with a GAN-like way of approximating this F-divergence that does not require likelihoods. Oh, question, yeah.
Why were we able to estimate the objective for GANs before, if GANs are an example of a F-divergence?
So we'll be using, the reason we were able to do it for, I guess, Jensen-Shannon divergence is exactly what we're going to see now, which is basically a way to kind of reduce this expectation, which looks like something that you might not be able to compute. Kind of like if you look at the Jensen-Shannon divergence, it looks like something you're not able to compute. But if you have an optimal discriminator, intuitively the optimal discriminator computes these density ratios for you. And so that's how you get around it. Kind of like you are sort of offloading this problem of computing the density ratios to a discriminator. And this might be good or bad, but the hope is that neural networks seem to work really well for kind of supervised learning classification problems. And so we might be able to come up with reasonable estimates of these density ratios by training a classifier. Because to do well at classification, if you're trying to classify real samples from fake samples, you essentially need to estimate that. Like the optimal classifier requires you to know for every x, how likely is this point to come from one versus the other. And so that's kind of like the trick. Cool. So the machinery for doing this goes through something called the Fenchel conjugate or the convex conjugate of a function, which is defined like this. If you have a function f, you can obtain another function f star, which is called the convex conjugate of f by using the following expression. So f star is now going to be a function of t, and the value of f star at t is the solution to basically this optimization problem. where you're taking the supremum over all the u's in the domain of F, and then you have this kind of a relatively simple objective, which is just ut minus f of u. And so, seems a little bit random, but this convex conjugate has a bunch of useful properties. In particular, it's a convex function, even when f is not. And the reason is that the argument here in the supremum as a function of t is just basically a bunch of affine functions. It's just linear in t. And so the supremum of a bunch of convex functions is also convex. And so, you can think of this as the supremum of a collection of functions that are indexed by u. And but as a function of t, they are all very simple. They're just linear functions. And then when you take the supremum of a bunch of convex functions, you get something convex. The other interesting property that we're going to use is that we can look at the conjugate of the conjugate, which we're going to denote as f star, which is just what you get if you take the conjugate of a function f. And again, you basically just apply the same definition, but now the function f becomes f star. And it turns out that this convex conjugate is a lower bound to the original function f. So it's always less than or equal to f. And so the proof is actually very simple. You can kind of see that by the definition that we have up here, we have that for every choice of t, f star is at least as large as ut minus f of u, because it's the supremum, so it has to be at least as large at all the possible values that you can get for any choice of u. And if you rearrange, you can move the f on the other side, and you can write it as f of u is at least as large as ut minus f star, if you just move this and this on the other side. And now this definition means that f of u, because this holds for any t and for every u, then it means that f of u is at least as large as the supremum of ut minus f star of t, the convex conjugate, which is exactly the definition that we want, right? That's exactly the conjugate of the conjugate, f double star. And so we see that this conjugate of the conjugate is always less than or equal to the original function that we started with. And it turns out that when f is convex, then the conjugate of the conjugate is actually equal to the original function. If you start with a function, you can get the conjugate, and then if you conjugate again, you go back to the original function when f is convex. Now, the reason this is going to be useful is that this is kind of like going to be similar to the elbow, the evidence lower bound. What we're going to do is we're going to try to write down f in our definition of the F-divergence in terms of the conjugate. And we're going to get bounds on the value of the F-divergence by going through this characterization of the f function and an F-divergence in terms of this convex conjugate. And so that's basically the kind of like idea that underlies this framework for training generative models based on F-divergences through a GAN-like objective. So what we do is we have the original definition of the F-divergence, which depends on this density ratio that we don't have access to. We can equivalently, because f is convex, we can equivalently rewrite this in terms of the conjugate, which is just the conjugate of the conjugate, f double star, which by definition is just this supremum. Recall that we're evaluating f double star at the density ratio, so we can write f double star as the supremum of t argument minus f star evaluated at t. That's just the definition of the conjugate of the conjugate. And now this is starting to look like something a little bit more manageable, because we see that the density ratio that before was sort of like inside the argument of this f function that we didn't know how to handle, now kind of like it becomes a linear dependence on the density ratio. Like now, except for this unknowing supremum, then the dependence on Px over Qx is sort of like outside the argument of f, which will allow us to basically simplify things. Now, what you can see is that for every value of x, there is going to be a different value of the density ratio, and there is going to be a different value of t that achieves the supremum. And we can denote that supremum that you get for any particular x as t star of x. So this is just the value of the supremum when we're looking at data point x. And this is kind of like going to be what the discriminator is going to do later on. But you see that now we have an expression that is not too bad. It's an expectation with respect to Q that we know sort of like how to approximate using samples. And now we have the density ratio is kind of like outside the argument of this f function that we use to score them. And what this means is that basically, if you expand it, it will look something like this. The expectation with respect to Q is just an integral where every x is weighted using Q of x. And now, if you simplify it further, and you notice that this Q of x simplifies with this Q of x, this whole expression basically just looks like the difference of two expectations. There is an expectation with respect to P, and there is an expectation with respect to Q, but that's sort of like similar to what we had in the GAN framework, where we had an expectation of something with respect to the data distribution, an expectation of something else with respect to the model distribution, and that was giving us our estimate of the Jensen-Shannon divergence in that case. You can see that the same sort of idea holds more generally for different choices of f. But, yeah, question?
What is supremum?
The supremum is the same as the max, basically. It's just like, it's the domain. There does not necessarily exist a max, so it's a little bit of a technicality, but think of it as the max, basically.
So where there is a star sign for the Tx function?
I'm just denoting it T star because this is basically but it's just a way of denoting the value, what the supremum over T evaluates to for any particular x. There's going to be a value of T that achieves the supremum. I'm just going to denote it T star. Other questions? Yeah.
In this case, don't we still have to evaluate P-offs, which is
So the good thing is that this is an expectation. I mean, it looks like, it still depends on P of x. But if you look at the formula, this is basically, do I have it? Okay, maybe it comes up later. But it's an expectation with respect to P of x. Okay. And that you can approximate by taking samples, which we have because you have a training set. Yeah.
I saw that you went ahead and you pull out the supremum from the T's, and how do you parameterize or how do you represent T?
Yeah. So then the next step is that basically equivalently, you can just say, well, there is going to be some function that we're going to call T that gives you this optimal value of T star for every x. This doesn't change anything. Basically, for every x, there is an optimal choice of T, which comes from the supremum. Here I'm denoting it T star. Equivalently, you can say, okay, there is a function T that takes x as an input and gives you as an output the supremum of that definition of the convex conjugate. And then that's where you get the bound, is you can say, well, I cannot, this would require you sort of like an arbitrarily flexible function t that can take any x and map it to the solution to this optimization problem. But recall, this has a little bit of the flavor of a VAE, amortized inference in a VAE, where you have this encoder that is supposed to take x as an input and then map it to the optimal variational parameters, kind of like solving an optimization problem for you. This kind of has the same flavor. But what we can say is, well, you can always optimize over a set of functions, an arbitrary set of functions, a set of neural networks, and that would give you a lower bound on this F-divergence. So if instead of optimizing over all possible functions, you optimize over a set of neural network architectures that you're willing to consider, you're always going to get something that is less than or equal, because you might not have sufficient flexibility for mapping x to the corresponding value t star of x that you would have gotten if you could actually solve this optimization problem exactly. But you definitely get a lower bound for any choice of this family of mappings that you use to map data points to essentially something that looks like an estimate of the density ratio. And the more flexible this family script T of neural networks you can choose, then the tighter this inequality is. So the better of an approximation you get to the true value of the F-divergence that you started with. And back to your question of, okay, does this depend? It looks like this still depends on P and this one still depends on Q. You notice that these two are just expectations with respect to P and Q, which in our case will be the data distribution and the model distribution. And so this is essentially the same as a GAN, generative adversarial network training objective. I remember the objective that we were using for training a GAN is the min over G, and then we had the max over the discriminator of something that looked a lot like this. So you were sort of like evaluating the discriminator on the data sample, you were evaluating the discriminator on the fake samples, and you were trying to kind of distinguish them, contrast them through the cross-entropy loss. And here we get something that has a very similar flavor, where we're sort of like evaluating this discriminator T over data samples, over model samples, and we're trying to essentially distinguish them by maximizing that quantity.
T is going to be our trainable neural network.
Yes, so when we do this optimization over T in the script T, that's going to be where we optimize the discriminator or a critic kind of. And this script T is going to be a family of neural networks that we're going to use to choose T from.
Usually we represent our data distribution as P and the proposed distribution P theta as Q, right?
Yeah.
So for this to hold, we don't need the discriminator to be optimal.
So if you want tight, if you want to have an exact estimate of the F-divergence, then the discriminator has to be optimal. But if you don't, then you know that you're going to get at least a lower bound. So the lower bound part holds even if the discriminator is not necessarily optimal.
Don't you sort of inherit the same problems with like we discussed, having a lower bound? Don't you inherit it from before? If you don't have an optimal discriminator, you just inherit all the problems here, right?
Yeah, it's a problem in the sense that you're optimizing a bound, so it might or might not be the right thing to do. And this is a lower bound, so minimizing a lower bound might not be going in the right direction. And so, yeah, you still have those problems. So in that sense, it's approximately optimizing an F-divergence. If you could somehow optimize over all possible discriminators, then, and I guess you had infinite data and you were able to actually solve this optimization problem perfectly, then you could really optimize an F-divergence. But in practice, no, there is always approximations.
So in this setting, not with the discriminator setting, T is supposed to represent the maximal value of x that exceeds the function? Like what is p here? The supremum definition is supposed to use it.
Yeah, so it's supposed to essentially, it's essentially computing the conjugate of the conjugate of f, and it kind of like corresponds to finding supporting hyperplanes. So you're kind of like encoding the graph of the function as kind of like a convex hull, and that optimization problem is kind of like trying to find essentially tangent to the graph of the function. So that's essentially what's going on in that optimization problem.
Has anyone thought about how to do this for an upper bound instead of a lower bound? Because I feel like it's more natural to minimize an upper bound, right?
Yeah. So yeah, that's kind of like what I was saying, that in the outer optimization problem, you're going to be minimizing this, and then this is a bound that kind of like goes in the wrong direction. And unfortunately, getting upper bounds is much harder. There is work where people have tried to come up with bounds, especially as it relates to. It turns out that you need to do something similar if you want to estimate mutual information between random variables, which also basically involves some kind of estimating density ratios. And there is literature on trying to get bounds there, but nothing that works particularly well.
How is it better than like KL, they're just using KL divergence?
Training with respect to this versus KL divergence? Is that the question?
Oh, it's because it doesn't need
it doesn't need likelihood, and it achieves as we know, like KL divergence is all based on compression, which might or might not be what you want. These other F divergences are not necessarily capturing a compression-like objective. Because you're evaluating the density ratios in a different way. Like you don't just care about the log of the density ratios, you can plug in different sort of Fs that captures different preferences for how close is the model density ratios to the true density ratio. That's kind of like captured through F, and that gives you more flexibility basically in defining a loss function for training your model.
Which term in this pair of expectations, like in the GAN word, corresponds to the discriminator and generator derivative?
Yeah, so depends what you want to choose. So it could either be P is data and Q is model, or it could be vice versa. In both cases, you would end up with something that you can handle in the sense that it's a different of two expectations. And depending, do you want KL data model or do you want KL model data? Depending on what you want, you need to choose the right order and the right F that gives you the right thing. So it could be both. It doesn't matter for the perspective of this. It's just the difference of two expectations. You have samples from both, and you can estimate both of them. Yeah, Monte Carlo.
Yeah. Could you explain one more time how we went from T star X to having a supremum over all T, from the fourth last step to the third last step?
So how do we go from the supremum to the T star? Okay, this one.
Yeah.
Yeah, so this one is basically saying that there is going to be an optimal T star for every X. And if you are allowed to have an arbitrary function, an arbitrarily complicated function that basically just maps every X to the corresponding T star of X, then you get the same sort of result. So you could say, for every X, I'm going to choose a T star, or you could say I'm going to first choose a function that maps X's to T stars, and to the extent that this function can do whatever you want, then there is no difference. You can kind of like memorize all the T stars into a table and then encode that table into the function T. And so choosing the function or choosing the individual that basically outputs of the functions across the different X's is actually the same thing.
Like the higher level motivation here that when we look at GANs, you looked at the optimal discriminator, we got the scale and the scale thing. But now if we go another way, we look at different functions here that we might get different discriminators.
Yeah, essentially yes. That's the way to think about it. This is a generalization. Like in the GAN framework, the original simple thing, we kind of started from an expression that looked like this, and then we showed, oh, by the way, it gives you the Jensen-Shannon divergence. this is kind of showing how you can actually start from any F-divergence you want, and you can get a loss that kind of looks like a GAN. And by the way, if you were to start from Jensen-Shannon divergence, you would get exactly the GAN loss that we started with, right, up to shifts and scales. Cool. And so, yeah, the thing to note is that the lower bound is likelihood free in the sense that you can evaluate just based on samples. And once you have this kind of like lower bound on the F divergence, you can get a GAN-like objective as follows. You can choose an F divergence of your choice. You let, let's say, P to be the data distribution, Q to be the model distribution defined implicitly through some generator G. And then you parameterize both using neural networks. So let's say you have a set of neural networks with weights phi that define this function T that you have on the outside, the discriminator basically. And then you have some parameters that define the generator G. And then you have an F-GAN training objective, which is very similar to what we had before. It's again a minimax kind of optimization problem, where there is the inner maximization problem over phi, where you're trying to find a good approximation to the F divergence by maximizing, kind of trying to solve this optimization problem as well as you can, by trying to find weights phi that makes this expression as big as possible. And again, it is no longer kind of cross entropy, but it's something quite similar. And then on the outside, you have a minimization over theta because you're trying to minimize the F divergence between the model and the data distribution. And so just like in the GAN setting, we have the fake samples that are coming from this implicit distribution defined by a generator with parameters theta. And you can try to choose the parameters theta that minimize this expression. And this, it's basically the same as what we had in the, if you were to choose the Jensen-Shannon divergence, that this would correspond to what we had before. But fundamentally what's going on here is that there is a generator that's trying to minimize the divergence estimate, and there is a discriminator that's trying to come up with the best possible sort of bound on that F divergence.
So if I do take F to be pure divergence, can we still show that, like, using this equation, it still distills down to maximal, like,
So it's not going to give you exactly maximum likelihood because it's an approximation unless you have infinitely flexible kind of discriminators. What people have shown is that if you were to, in the original F-GAN paper, they basically tested a bunch of different Fs for F divergences. And what they've shown is that if you choose the F corresponding to KL divergence, then you tend to get samples that indeed give you better likelihoods, as you would expect, because you're kind of like approximating the KL divergence. But as we kind of like discussed, that's not necessarily the one that gives you the best sample quality, and you might be getting better sample quality if you were to choose different Fs in that paper. Cool. So that's the kind of high-level takeaway. You're not restricted to KL divergence, exact KL divergence, or Jensen-Shannon divergence. You can actually plug in other F divergences, and using the F-GAN training objective, you can still approximately optimize that notion of that divergence. Now, the other thing that you can do using a very similar kind of machinery is optimize yet a different notion of divergence, which is based on this idea called the Wasserstein GAN. And the motivation for moving beyond F divergences is that F divergences are nice, they're very powerful, but there are issues when the distributions P and Q don't share, kind of like they have, let's say, disjoint supports, which can happen, especially early on in training. The samples coming from your generator could be very, very different from the ones that are in the training set. And if that happens, you can have this weird kind of discontinuity where the KL divergence is kind of like a constant, maybe infinity or something, and then suddenly shifts to some better value the moment the supports kind of like match. And that's a problem because during training, you don't get sort of like good signal to go in the direction of trying to make the support of your model distribution close to the support of the data distribution. And you can kind of see an example here. Imagine that you have a super simple kind of data distribution where all the probability mass is at 0. And then you have a model distribution where you put all the probability mass at this point theta. Right? And so if theta is 0, then the two distributions are the same. But if theta is different from 0, then these two distributions don't share any, the supports are different. Right? If you look at, let's say, the KL divergence, it's going to be 0 if the distributions match, and it's going to be infinity for any other choice of theta. So if you're trying to train this generative adversarial network by kind of like optimizing theta to reduce the KL divergence, you're not going to get any signal until you hit the exact right value that you're looking for. And if you look at the Jensen-Shannon divergence, you have a similar problem where basically it's 0 if you have the right value, and then it's a constant for when you have the wrong value. But again, there is no signal. There is no notion that, you know, theta 0.5 is better than theta 10. Ideally, that's something you would want, because if you have that, then you can kind of do gradient descent and you can try to move your theta closer and closer to the value you want. But this sort of F divergences can have trouble with these situations. And so the idea is to try to think about other notions of distance or divergences that work even when P and Q have disjoint support. And the support is just the set with of points that have non-zero probability under P or Q. And so that the kind of like one way to do this is to use this thing called the Wasserstein or the Earth mover distance. And the intuition is something like this. Like, let's say that you have two distributions, P and Q, and you can think of and they are just, let's say, one-dimensionals. So you have the densities that I'm showing there, and they're just mixtures of Gaussians in this case. And you can ask, how similar are P and Q? And one reasonable way of comparing how similar P and Q are is to say, if you think of the probability mass as being kind of piles of earth or piles of dirt that you have laying out on this x-axis, you can imagine how much effort would it take you if you were to shovel all this dirt from this configuration to this other configuration. And intuitively, the further away you have to move this earth, the more cost you pay, because you have to, it takes more time. And, P and Q, they are both normalized. So kind of like the amount of earth that you have on the left is the same as the amount you have on the right. But kind of like the more similar, if P and Q are the same, then you don't have to do any work. If the probability mass under Q is very far from the one under P, then you have to do a lot of work because you have to move all this earth from various points where you have it on the left to the points where you have it on the right. And the good thing about this is that we'll see that it can handle situations where the supports are different. This kind of definition doesn't care if the supports of P and Q are disjoint or not, and it defines a very natural notion of distance that varies smoothly as you change the shape of P and Q. And the way to mathematically write down this intuition of looking at the cost of transporting Earth from configuration P to configuration Q is to set up an optimization problem, which looks like this. So the Wasserstein distance between P and Q is going to be this infimum, which think of it as the minimum, basically. And this infimum is over all joint probability distributions over X and Y. You can think of X as being the distribution, P being defined over X and Q being defined over Y, let's say. And so you look at joint distributions over X and Y such that the marginal over X matches P and the marginal over y matches q. And what you do is, over all these joint probability distributions that you have here, that you're optimizing over, you look at the expected cost that you get when you draw x and y from this joint distribution. And the cost is the thing that we talked about, which is basically how much effort it takes to go from x to y. And in this case, it's measured with this L1 distance. You can choose other choices, but for now, you can think of it basically the absolute value in 1D of x minus y. And you can think of this gamma xy, which is a joint distribution over x and y, as basically telling you how much probability I'm moving from x to y. And so what this is saying is that this condition here, that the marginal over x is p of x, this is saying that at the beginning, like you can't move more probability mass than what you started from at x. And the fact that the marginal over y is qy means that the final kind of result, the amount of Earth that you find at position y is indeed the one that you want to get, sort of like in the final configuration, which is the one you're trying to get to. And this objective function here is telling you what is the cost of moving Earth basically from x to y. So equivalently, you can think of the conditional distribution of y given x as telling you which fraction of the Earth that I have at location x am I going to move to the different y's. And so you can see that then if you look at this expectation, this is telling you in expectation how much is this going to cost you. Well, you look at x, you look at the y's you're moving the Earth to, you look at the difference between the two, and that tells you how much it costs you to, for a given x, if you take the expectation with respect to gamma y given x, it's telling you the cost of moving all the probability mass that you have at x to the places you want it to move it to, which, because of this constraint here, it has to match the final result that you want. And so that's basically the optimization problem that defines this intuition of telling us how much work do you have to do if you want to move this, you want to morph this probability distribution here into the probability distribution Q that you have as an outcome. And just to get a sense of what this looks like in the previous example where we had this, let's say, data distribution where all the probability mass is at 0, and this model distribution where all the probability mass is at theta. This one, the KL divergence between these two objects is not very useful. But if you think about what is the Earth mover distance here, how much work do you need to do if you want to move all the probability mass from here to here? Basically, you have a big spike at 0 on the left, and then you have a big spike at theta on the right. How much work do you need to do?
X minus y theta.
Theta, yeah. So it's the absolute value of theta, technically. And so you can see that now it's starting to be more reasonable in the sense that the closer q theta is to the target, p, the smaller this divergence is, which you might expect might be a much better kind of like learning objective because you have much better gradients. You kind of like you have a notion of how close you are, how much progress you're making towards achieving your goal, and to the extent that you can really compute this thing, and we'll see how to do that. This would be a pretty good sort of like learning objective to use.
Confused about definition. So P and Q are the distribution, or two distributions. Are you saying we can have multiple joint distributions of P and Q?
Yeah, there is an infinite number of joint distributions that have given marginals. If you think about it, this is actually a pretty mild kind of set of constraints. It's just saying that for every x, the marginal under gamma has to match the distribution that you started from. So this is kind of like saying that if you think of gamma x comma y as the amount of earth that is moved from X to Y. This is sort of saying that the total amount of earth that you, or actually that is, yeah, that the total amount of earth that you move has to be the amount that you had to begin with. And this is sort of saying that the other constraint is sort of like saying that if you look at the amount of earth that you get at the end, after you've moved everything from all the various x's, it has to match what you want, which is the final result, the final Q of Y, which is the amount of earth that you want after you've done all this transport, or after you've moved all the probability mass. So yeah, if you have two random variables, you can think about many different joint distributions with the same marginals. Like even if you think about two binary random variables, like these two random variables could be independent, they could be highly dependent, and the joint distribution is what tells you how they are related to each other. So there is many joint distributions with the same marginals. And in this case, the relationship between them is kind of like telling you how much, how coupled they are and where you're going to move sort of like probability mass from one to the other. Yep.
Can you go over what exactly does the term inside the expectation indicate?
Yeah. So basically what this is saying is it's just the L1 norm, which in 1D you can think of it as just the absolute value of x minus y. And this is just saying that when x and y are far away, they're going to pay a higher cost because transporting from here to Palo Alto is cheaper than from here to San Francisco. And so you can think of if the x-axis is kind of like measured in kilometers or something, and then you would x minus y is just like the distance that you have to travel to go from one point to the other. And so ideally, you would want to choose a gamma such that when you sample from it, x and y are very close to each other. So you minimize the amount of work that you have to do. But that's non-trivial because you also have to satisfy these constraints that sort of like at the end of the day, you've moved all the probability mass that you have to move, and you get this Q configuration as a final result, which is this constraint that is saying the marginal over y is Q of y. And this constraint is just saying, oh, you cannot create Earth out of nowhere. You have to move the Earth that you started from. Like you have to go from the configuration that you have on the left, which is P, to the configuration that you have on the right, which is Q. And these constraints here on the marginals are basically just saying that that's the initial condition, that's the final condition, that's the cost that you incur whenever you move Earth from X to Y. The inf is think of it as the minimum, yeah. And so again, basically you want to choose a gamma y given x that puts as much probability mass on y's that are close to x as possible. But then you not always can do it because sometimes you do have to move away. Like if you have to move probability mass out here and you didn't have any, then you have to sort of take it somewhere. And this optimization problem tells you what's the optimal way of, what's the optimal transport plan that moves the mass from one setting to the other. And again, we're basically in a situation where, the original objective function is reasonable, makes sense, it would be good to optimize, but it looks like not something we can actually compute because, as usual, P and Q should be a model and a data distribution. We don't know how to evaluate probabilities according to one or the other, so that doesn't look like something we can optimize. But it turns out that there is a variational characterization, or there is a way to basically write it down as the solution of an optimization problem that we can then approximate using some kind of discriminator, some kind of neural network. And it's possible to show that this Wasserstein distance or Earth mover distance is equal to the solution to this optimization problem, where you sort of have a difference of expectations, one with respect to P and one with respect to Q. So again, it's very similar to the GAN setting. And the only difference is that now what we're doing is we're optimizing over functions that have Lipschitz constant 1, which basically means you need to optimize over all functions that basically don't change too rapidly. And so the solution to this optimization problem over these scalar functions f is actually equal to the Wasserstein distance. And notice here we don't have f stars anymore. This is really just the difference in expectations between p and q. And so if you didn't have any constraint, then you could make that thing kind of blow up very easily, because sort of like you could just pick a point where the probabilities are different, and then you could just increase the value of f at that point arbitrarily, and then you could make this this objective here extremely large or extremely small. But you cannot do it. You cannot choose an arbitrary kind of function f because you have this constraint that basically the shape of f cannot change too rapidly. Has to have Lipschitz constant 1, which basically means that if you go through the graph of f and you take any 2 points, x and y, the kind of slope that you see is bounded by 1 essentially. And again, this sort of optimization problem by itself is not quite something we can solve, but in practice, what you can do is you can approximate the inner this optimization problem over all kind of discriminators that are kind of like trying to tell you, think about it, what is this objective doing? You're kind of like looking for points where the probability mass under P and Q is different. So you can find these points, then you can increase the value of F, and you can kind of get a high value in that difference of expectations. And so you can approximate that problem of trying to find X's that are given different probabilities on their model and data by training a neural network, which is again going to be some kind of discriminator. And at this point, there is again no cross-entropy loss. You're just trying to find a network that can take high values on the data points and low values on the fake data. And to enforce the Lipschitzness, enforcing Lipschitzness is hard, but in practice, what you can do is, as usual, you don't want this network to be arbitrarily changing too fast, too much. And then in practice, what you do is you would either clip the weights or you would enforce a penalty on the gradient of this discriminator so that, again, it cannot change too much, cannot change too rapidly.
You mentioned this. I was trying to understand the relationship between the duality and the Earth mover distance. So are they equivalent?
So the Earth mover distance is this quantity you have on the left. So to the extent that you could solve this optimization problem on the right, then you would be able to compute exactly the Earth mover distance.
Okay. So basically the optimize the solutions on the right hand side were equivalent to the...
Yeah. And intuitively, kind of like this function f is telling you, where there is a discrepancy in probability mass between P and Q. So if there are x's that are given different probabilities under P and Q, then f will try to choose a large value ideally. But then because of this Lipschitzness constraint, then you cannot make it arbitrarily big, like you cannot go to infinity. And so you have to somehow be smooth and at the same time, try to find differences between P and Q.
Is this optimization problem guaranteed to find the solutions?
So if you can solve this one, yes, will give you exactly the Wasserstein. The problem is that in practice you cannot, you kind of like before, like in the F-GAN setting, you can't really optimize that. And so in practice you would use approximations where you just use some sort of discriminator and you try to make sure that the discriminator is not too powerful, and you try to restrict basically how powerful the discriminator is by either, for example, trying to have a penalty term on the gradient of with respect to the inputs of the discriminator so that it cannot change too much. And this doesn't give you bounds. So unlike the F-divergence setting, this is just an approximation. It doesn't necessarily give you bounds.
So to clarify, we have no guarantee that the Lipschitz constant will be 1, right?
Yeah.
Okay.
Yeah.
it's very interesting to me. Like, even though the math derivation are very different, but the end objective, they all look awfully similar to each other.
Yeah, so they're all based on the very similar idea where you're kind of like trying to find a witness function, a discriminator, some kind of classifier that is trying to distinguish samples coming from P from samples coming from Q, and depending, you have to restrict what this witness function or this classifier does in some way, or you change the way you're scoring what this classifier does, and depending on how you do that, you measure similarity basically in different ways. And if you restrict this discriminator to have a Lipschitz constant of almost 1, then you get Wasserstein. If you use an arbitrary function, but then you score it with respect to that F star, then you get an F-divergence, and so forth, yeah. But the main advantage of this is that it's much easier to train, so in practice this is very often used. And you can kind of see an example here where you can imagine a setting where you have real data that is just a Gaussian that is kind of here. So you see all the samples that are coming, that are these blue dots. They're kind of like lying around here. And then you have a model. Let's say you start out with a bad initialization for your generator, and most of your samples are again a Gaussian, but somehow the means are different. And so all your samples are here, these green dots. And if you get the discriminator will have a very good job at distinguishing between the blue samples and the green samples, and it will be a sigmoid, but it's extremely steep. So, basically everything to the left here will be classified as real, everything to the right will be classified as fake, but it's almost entirely flat. And so when you think about trying to figure out, when you update the generator to try to fool the discriminator, you don't get a whole lot of signal in terms of like moving, in which direction should you move these data points. Because the red curve is too flat. And so it's very tricky to actually get this model to learn and being able to learn how to push the data points, the fake data points towards the right. But if you think about the Wasserstein GAN critic, which is just the discriminator, it's almost like a linear function. It's this light blue curve. And if you are from the perspective of the generator and you're trying to kind of reduce the same objective function that was being optimized by the critic, you have a much better kind of learning signal to push your data points to the left. And you kind of know that, yeah, these data points out here are much better than the data points out there.
How we calculate this, the Wasserstein GAN curve, like the critic?
Well, in this case, I guess you can even do it in closed form. I don't know if they did it. You could probably also approximate it somehow, but if it's just two Gaussians, I think you can do it in closed form.
Well, why are the slopes kind of different? Like they have different direction. Discriminator.
Yeah, so I guess you would still try to minimize so this is just the decision boundary, which is not, well, yeah, I guess you would still you would try to, yeah, because it would be the opposite. So you're trying to make it fake, so you would still push towards the left. And from the perspective of the W-GAN, you would still try to minimize. From the the perspective, you will minimize this expression that you have inside. And so again, you would push the points to the left because this blue curve, the light blue curve, goes down. And so I think it's just that it's plotting probability of fake instead of plotting probability of real. So that's why it's going in the wrong direction. Okay, yeah.
Can you go over again how like using this form of a divergence is better than the F-divergence?
Yeah, so the reason you can actually see it here, and it's just that you have basically better learning signal, and it's kind of similar to what we were talking about here, that if the distributions are too different, then with respect to KL divergence, you might not have good enough signal that tells you, oh, like if you put in this case, putting the probability mass at 1/2 is better than putting the probability mass at 10. Like with respect to the Wasserstein, this would show up because there would be a difference between those two settings, and 1/2 is closer to the ground truth than 10. And so you would be able to do gradient descent on that objective with respect to theta, and you would get closer and closer. With respect to KL, you don't quite see it. And in practice, you can also see it here, where basically doing optimization from the generator perspective, doing optimization by minimizing the light blue curve is much easier than trying to kind of fool the discriminator in the regular GAN setting, because this kind of like, there is vanishing gradients and it's too flat.
How we understand like this Wasserstein GANs kind of have a better statistics, like testing something, like.
Yeah, I don't know if you can formally prove that it's more powerful than a regular GAN. I think it probably.
It's like a regular GAN sort of tell if it's a fake or not, right? But this kind of shows you the distance between the.
Yeah, they're measuring distance in a different way, and I don't know in general. You could say you would probably have to make some assumptions on P and Q to say which one is better and which one is worse. I think in general, I think from this, it's more like if you had access to infinitely powerful discriminators, I think in that world, I think both would probably work. I think in practice, you always have approximations and you are optimizing over restricted families of discriminators, and you have this minimax thing where you cannot actually solve the problems to optimality. And it turns out that optimizing the Wasserstein type objective is much more stable in practice. Cool. Maybe the last thing we can briefly talk about is how to actually inferring latent representations in GANs. This is going to be a bit of a shift in terms of the topic, but once you train a GAN, you have these latent variables that are mapped to observed variables, and you might wonder, it kind of looks like a VAE. To what extent are you able to recover Z given X? Let's say if you wanted features or something like that. And one way to do it, the problem is that it's no longer an invertible mapping, and you don't have an encoder, right? So in the flow mapping setting, you just invert the generator. So given an X, you figure out what was the Z that would be mapped to that X. In the variational autoencoder, you have the inference model, you have the encoder that is doing that job for you. In a GAN, you don't quite have it. So one way to get features from a GAN is to actually look at the discriminator. So the discriminator is trying to distinguish real data from fake data. So presumably to do well at the job, it has to figure out interesting features of the data. And so you can try to take the discriminator and fine tune it on different tasks, or take the representations that you get sort of like towards the end of the neural network and hope that those features are actually useful for other kinds of tasks. If they were helpful for distinguishing real data from fake data, they might work for other tasks as well. But if you want to get the Z variables from the discriminator, from the generator, kind of like in the VAE, then you need a different learning algorithm. And the problem is that in a regular GAN, you're basically just looking at the X part. And somehow we need to change the training objective to also look at the Z part, at the latent variables. And the way to do it is to basically change the way you set up these two sample tests, or these likelihood-free learning objectives, to not only compare the X samples that you get from the model to the real data samples, but to also look at the representations, the kind of Z's that produced the samples that you see. And the thing is that when you sample from the model, you get to see both the X and the Z part, because you're sampling them yourself. But in the data, you only get to see the X. There is no corresponding Z. And so the way to do it is to essentially, just like in a VAE, introduce an encoder kind of network that will map X to the corresponding latent representation Z. And so the architecture looks like this. It's called the bi-GAN, because it sort of like it goes in two directions. So you have latent features that get mapped to data through the generator, and then you have data that gets mapped to latent features through some encoder network. And then the job of the discriminator is to kind of like not only distinguish GZ from X, fake samples from real samples, but now the discriminator is going to try to distinguish fake samples with the latent variables from the model from real samples and latent variables inferred from the encoder. So it's going to work on pairs of inputs, X and Z, where sometimes the X's are real, sometimes they're generated by the model, and same thing. Sometimes the Z are real, they're produced from the prior, and sometimes they're produced by feeding real data to the encoder. And then basically everything is the same. Then you train the generator trying to fool the discriminator, you train the encoder, and you train the discriminator trying to distinguish the samples. And to the extent that this works, so the discriminator observes these pairs, and the discriminator is trying to do as well as it can at distinguishing these two pairs. And after training, basically you can get the samples from G, and you use the encoder to get the latent representations. And yeah, that's sort of like the idea. It's pretty simple. It's kind of like an extension of GANs, where you have another mapping, which is also deterministic, going from data to latent features, and then you let the discriminator operate not only on data, but on data, latents. And so to the extent that the discriminator cannot distinguish the Z's that are produced by the generated procedure from the Z's that are produced by the encoder, then you might expect that the encoder is producing latent representations that are similar to the one the GANs would have used for generating a data point. And so effectively the encoder is inverting the generative procedure. So it's very similar to a variational autoencoder, except that E is a deterministic mapping and is not trained by minimizing KL divergences, like in the elbow, but is trained by minimizing some kind of two-sample test that is being optimized by a discriminator. And but the same sort of it's the same sort of high-level intuition. Yeah.
Is that a concatenation of X and EX that is being fed through the distribution? Okay.
Yes, it's the concatenation. So you need to be able to distinguish pairs of real data, features produced by the encoder, from fake data, real features produced from the prior. So if you cannot distinguish them, then the features that you get from the encoder E of X are going to be very similar to the Z's that were actually used for generating data points. And so that's how the encoder is trained. Everything is trained sort of like adversarial.
So the discriminator will see latents and the images?
Yeah. Yeah, cis pairs.
And you mentioned the pair, they are basically 4 different combinations, like the real image and the deterministic feature, the encoded feature with generated image, the encoded feature with the original image.
In this version, no, there's only 2 options. But you could imagine a version where there is you're trying to enforce something stronger, where maybe you want it's more like a cycle consistency that I guess we didn't have time to talk about today. Here there's only 2. There is basically samples from the model and corresponding latents versus real data and corresponding latents.
It says after training is complete, new samples are generated via G and latent representations inferred via Z, via E. But when we generate the new samples with G, didn't we first come up with the latent representation? why do we still need to infer it?
So that's meant to be on real data. So let's say that then you want to do transfer learning, or you want to do semi-supervised learning, or you want to do clustering or something. How do you get the features from a data point X? You don't use G because you don't know how to invert it, but you've trained a separate model, this encoder model that is basically trained to invert G. And so on real data, test time, you just use E to get the corresponding latents. Two different, kind of like a VAE, two different pieces that are trained together to sort of fool a discriminator. In this case, instead of minimizing an elbow.
There's something hard about that, like in this graph, where do we sample the Z's from?
Z's is all the same. They're sampled from a prior, so it's the same training as a GAN. So the Z part doesn't change. So the Z's from the top half, those are the Z's are from the prior, and then you pass them through the generator to produce data.
Okay, so we're just training E to make it map those to map the real images to the prior.
Essentially, yes. Except that in a VAE, that matching is done via KL divergence. Here, that matching is done adversarially, basically. So the outputs of the encoder should be indistinguishable from Z's that are sampled from the prior, where indistinguishable is measured not with respect to KL, and now it's measured with respect to a discriminator should not be able to distinguish that the stuff that comes out from the encoder when it's fed real data is different from the real latent variables that you sampled yourself from the prior. So it has the similar flavor to, if you remember at VAE, we had a very similar kind of intuition that what comes out from the encoder should be indistinguishable from the latents that you generate yourself. In that case, we were enforcing that indistinguishable using KL. Here we're using a two-sample test on a discriminator.
At inference time, the latents are sampled from E, right? Based on the last slide. But E requires an X as the input.
Yeah.
What do we input to E?
The image that you want to get representations for. So kind of like in a VAE, you have an X, you feed it through the encoder, and you get the corresponding latents, and then you do whatever you need to do. You do.
Yeah. But in VAE, at training time, like at inference time, we don't use the encoder at all, right?
In a VAE, at inference time, if you want to just generate, you don't use the encoder. But if you want to get features, then you still use the encoder, just like here.